So last week we talked about the map overlay, right? We talked about the data structure for the doubly connected edge list, right? Okay, so today the topic we are going to discuss is slightly different, but at the end you will find that they are also related. Okay, so what exactly is the problem that we are going to discuss? Okay, it's called Polygon Triangulation. Okay, as just like last week, okay, we are going to use a problem to motivate this research. Okay, so first let me make it clear. Okay, to triangulate polygon is a very, very important topic in computational geometry. Okay, it is because like you guys have played like video games, right? Okay, so when you know ray tracing. Do you know ray tracing? Nobody? In Chinese, it's called 光追. Yeah, 光追. That's basically like you know, some high-end game. Okay, there are some high-end games like they will generate like the object in three-dimensional, and it makes the idea to make the object realistic is, you know, they are going to, for example, like first, remember I told you guys, I mean last week, like no matter what the shape of the object is, okay, basically we use polygon to approximate the shape. Okay, I mean because we don't use curve, we use polygon, use like straight lines to small lines to approximate the curve, right? So every object will become some kind of polygon, right? But in order to make the object look realistic, okay, you need to make sure the object, what should I say, like it will reflect the light, just like you know, the regular object, okay, because regular object will reflect lights, okay, from the light source, of course, okay, and so even though we know like those objects are curved, right? Curved, so we can approximate the curve. I'm not saying like the edge. I'm saying like the surface. The surface is curved, right? So we are going to approximate those curves again by using small rectangles. Okay, that's exactly what we meant by triangulation. Okay, we are going to use a lot of triangles to approximate the curved surface. And then, because each triangle is flat, right? So it will be very easy. It will be very easy to calculate the light reflection of each small curve. Okay, that's the basic idea of ray tracing. Okay, of course, I'm not going to talk about ray tracing in detail because that's like they'll be covered in computer graphics. Okay, that's really not the topic of computational geometry. But I just want you guys to be aware. Okay, triangulation the concept of triangulation is a very, very important topic in computational geometry. We are going to revisit this topic actually several times. The first time is this problem, okay? This problem, I mean, the way we model this problem is, to be honest, I mean, the simplest way to do the triangulation. At a later chapters, you will see more and more complicated triangulation. We are going to put some restrictions in the triangulation process, okay? But for now, okay, yeah, this is the first triangulation. So, okay, so we are given, you know, because here we are. I mean, for the first slide, we are talking about the problem that motivates this research, this problem. So we are talking about, you know, guarding art gallery. Okay, you know art gallery, right? And you know, in order to guard the art gallery, okay, so you will have some paintings or maybe sculptures, like you know, in an open space, right? So in order to make sure, okay, no theft is going to steal the valuable pieces, okay, we normally will install cameras, right? We install cameras to make sure, like, you know, if somebody try to steal the art pieces, at least he will be caught. He or she will be caught, right? So, okay, but the issue is, okay, nowadays, like, the camera is really not that expensive, not anymore, okay? The camera, unless you are talking about very high-end camera, if you are talking about like internet-enabled like a camera, it's probably like less than $1,000 US, you can get one, okay? But assuming, okay, camera is expensive, and we would like to minimize the number of cameras. Okay, what approach should we use, or where to place those cameras when we want to minimize the number of cameras to be deployed in the art gallery? And you can imagine, okay, this camera, okay. Yeah, I mean, you could imagine that the camera can rotate. It can rotate, but you can see that, okay, because of those walls, some places, I mean, in the art gallery will not be covered by the camera. There will be some corners. There will not be. The camera just cannot see those places, right? Okay, but obviously, okay, if we want to consider the art gallery, okay, because the wall structure, okay, different art gallery may be very different, right? Okay, so now let's try to abstract this problem a little bit further, okay? Because after all, those wall structure is just too difficult to model. So we try to model, okay, we abstract that idea and model an art gallery by a simple polygon P, okay? So, I mean, first you may ask, you guys may know what polygon is, right? Okay, polygon, well, is formed by a number of sides, right? Each side is a line segment, right? Okay, But you know polygon. But what do we mean by simple polygon? Okay, a simple polygon is the polygons such that there is no hole inside the polygon, and the sides of the polygon do not intersect. Okay, so you don't see something like for example, this is not a simple polygon because there's a hole inside in it. Okay, and this is a simple polygon. Okay, the polygon doesn't have to be, a simple polygon doesn't have to be concave, convex. It doesn't have to be convex. Okay, 不用外凸啦. Okay, it could be, you could have like a shape like this. It's still simple because it doesn't contain hole. The edge of the polygon do not overlap. I mean, if you have something like this, then this is no longer a simple polygon because we have edges that overlap each other. Okay? So, just want you guys to be aware, okay? When we talk about simple polygon, what exactly we are talking about, okay? So, well, given an art gallery, okay, even with a very strange shape, I mean, I believe like a simple polygon, okay, although it's simple, it should be able to, because it could be like a zigzag, okay, I mean shape. So even for a simple polygon, okay, so the simple polygon should be enough to capture very strange shape of the art gallery already, right? So let's model an art gallery as a simple polygon. Then we want to find the minimum number of cameras to guard this art gallery or this simple polygon, okay? And we can pretty much prove that for arbitrary simple polygon, okay, to have a minimum number of camera, okay, to guard that, okay, for arbitrary simple polygon, is NP hard. Okay, NP hard means it's very difficult. Okay, I'm not saying it's unsolvable, but I'm saying like it takes exponential amount of time. Okay, if you can solve that, okay, you can reduce all the exponential algorithm into polynomial. Okay, I'm not saying, because NP hard just means like there's so far no easy solution for that so far. Okay, but in the future we don't know. But at least like just want you to be aware that this is a very difficult question. Very difficult question. I mean, as for like how to prove that this problem is NP hard. Okay, it is beyond the scope of this class. So I will not talk about that. If you are interested, I mean, there are references like at the end of the chapter. You can take a look to see like how to prove. I mean, this problem is NP hard. But anyway. So we want to place as small number of camera as possible, right? Okay, even though we may not be able to easily find the minimum number of camera, but we would like to reduce number of camera, that's for sure, right? Okay. so you know, the conservative approach, okay, is to place one camera at each vertex. Okay, I mean, no matter how complicated your simple polygon is, as long as you have one camera installed at the vertex, at each vertex. I mean, and remember, the camera can rotate, right? Okay, so it should cover all the area in your simple polygon, right? No matter how you draw it. I mean, remember, I told you, like, bring a piece of paper and try to, you can try draw different simple polygon to convince yourself that this approach, okay, this conservative approach, you know, works. Okay. So let's say, okay, our simple polygon has n vertices. Okay, has n vertices. Okay, then that means, okay, at most, n cameras will be enough, right? N cameras will be enough. Okay, but our question is, can we do better? Is it a better approach that we can reduce the number of camera? Okay, now we know n camera is enough, right? Okay, for a simple polygon with n vertices. Okay, but obviously, I mean, we don't think that's the number of camera. I mean, n number of camera is small enough. Oh, sorry. Okay. So here comes the triangulation part. Okay. Here, okay, we have a statement. Every simple polygon P admits a triangulation TP, and any triangulation of a simple polygon with n vertices consists of exactly n minus 2 triangles. You probably learned that, I mean, in your high school, or I'm not sure it's high school or junior high. I mean, if your polygon has n shape, okay, and you can, let's say if your polygon is convex, if you have a convex polygon, then it will be very easy to see that, you know, eventually you can triangulate it into n minus 2 triangle. I mean, let me just draw a very easy example. Do we have not any better. Okay, anyway. So you can just start from any vertex and then try to add the diagonal lines, right? And this will end up with some number of triangles, right? Right? You can use any vertex, okay, and you draw the diagonal lines to the vertex that are not, you know, next to this vertex. Then you can easily see that if you have n sides, if you have n vertices, this way will give you n minus 2 triangles, right? Okay, so for convex polygons, this is a very simple observation, and this statement obviously is true. But how about simple polygon? Because simple polygon, as I mentioned earlier, it is not necessarily convex, right? It could be, as I said, like zigzag, right? Okay. So how can we prove this statement is true? We can prove this statement, okay? We can prove this statement by induction. Okay. Well, I hope you still remember your something you have learned from your discrete math. I really need a marker, a good marker. Okay. So, okay, good. Okay, so first, let's say, okay, for n, we start from n equal to 3. I mean, because when number of vertex is less than 3, I mean, there's it's impossible to have triangle anyway, right? Okay, so the first, in order to have a triangle, you need to have at least 3 vertex. And for any simple polygon with only 3 vertex, well, you must. It must be a triangle anyway, right? There's no way you can draw anything else other than a triangle, right? So this is a base case. Okay, we have one triangle. Okay, which is, well, 3 minus 2, right? 3 minus 2, so this statement checks out for base cases, right? For base case. Okay? So induction hypothesis, okay, for n smaller than k, okay, we have n minus 2 triangles. Okay. For induction hypothesis, we don't need to prove, right? We just need to, claim that. Okay, and later we may need to use that. Okay. This is strong induction. Okay, strong induction, not like basic induction. Okay, so induction step. For n equal to k, okay, let's say we have a k number of vertices. Okay, so now, okay, your shape, it doesn't matter how ugly you look. Okay, say you have k vertices. Okay, you have k vertices. Okay, the interesting thing is like this, okay? If you are able to find a diagonal line to break your simple polygon into two simple polygons without, okay, of course this diagonal line should not intersect with any other, with any side, any edge in this simple polygon. If you are able to do that, for example, I mean, for this particular polygon, I can just use this one. I'm sorry, bad drawing. I can just use this because this is a diagonal line which does not intersect with any side, right? Any edge. Okay, I can use this one, I can use this one, I can use, there are many choices in this example, obviously. But if I am able to introduce a diagonal line, and this diagonal line does not intersect with any sides, then, okay, because if you look at one of them, okay, let's say this one, okay, contain, okay, let's say we have this, we have n, this one, let's say we have, well, we already use n, let's say this one we have p, number of vertices. Okay, this one has p number of vertices. Then this part must have what? How many? Because total we have k, right? Total of k. So, I mean, k remove p, but we need to add these two vertex back, right? Right? Because you cannot also remove these two vertices, right? So this one will have k minus p plus 2, right? Okay, so and obviously, no matter it's p or k minus p plus 2, both of them will be smaller than k, right? Both of them will be smaller than k, right? So that means we can use the induction hypothesis there. Okay, in other words, this polygon, this part will have p minus 2 number of triangles, right? And this part will have k minus p plus 2 minus 2. Okay, k minus p plus 2 minus 2 number of triangles, right? Right? So the total will be this one plus this one. You will see that, okay, this p minus 2, okay, cancel out this minus p plus 2. So total will be k minus 2. K minus 2. The total will be k minus 2 number of triangles. Okay? So we could use the induction to show that. But the issue is, remember, I told you, okay, if there's a diagonal line, then we can use this argument to make sure that the whole proof is valid, right? But the issue is, how do you have this diagonal line, right? How do you have this diagonal line? I mean, when you draw this diagonal line, we are assuming it is not intersecting with any other sides. But remember, I told you, you know, the simple polygon could be zigzag, right? So even, I mean,